Consider an open-top rail car of mass 1,000 kilograms rolling at 10 meters per second along a frictionless track. It begins to rain softly, the rain simply falling vertically, such that the rail car gains 10 kilograms per minute of water falling on it. So every minute it's 10 kilograms heavier. How fast is it moving half an hour after the rain starts? Think for a moment about a procedure you might use to find this final speed. From a Newtonian viewpoint, this problem is really quite hard. The issue is that we have a water droplet. So let's take one little water droplet. Oops. Which is about to hit the rail car. So the water droplet is moving down like that, and it's about to land on the wall, the rail car. Well, it has to be both stopped, right? So eventually, after hitting the wall, the rail car, it's got to be at rest vertically, but it's got to also end up starting to move with the rail car. For simplicity, we'll look at just the drop right before it hits the bottom of the tank while it's still empty, while the car's still empty. It gets a little weirder, but certainly no easier if there's already water in the car, so things are sloshing back and forth. But ultimately, it's got to be the floor of the car that stops it. Right? The car exerts a force upward on the drop to slow its descent and stop it, which means by Newton's third law, the droplet must be pushing back down. All right, so the rail car will actually press harder against the earth because it's being pushed against this tiny little droplet. It's even worse when you consider the horizontal motion. Right? The droplet was not moving horizontally when it hit the rail car, but now it is. So again, here's the droplet, and it was moving downward, and now a little bit later, it needs to be moving rightward. Why does it start moving rightward? Because the back of the rail car must have come up and hit it and given it a little push forward. Again, if there's water in the rail car, it might have hit some water that was moving over, but ultimately it's the back of the rail car that's pushing everything over. The back of the rail car pushes it until they have the same speed, at which point it no longer is push on it, they'll move together. But of course that means by third law, the drop pushes back on the car, so the car slows. The car and the drop come to the same speed, but it's a slower speed than we originally had. And finding that slower speed is going to be tricky. Even if we assume the horizontal forces are constant, which is not a great assumption, we'd have to figure out how long it takes the two things to come to the same speed, what accelerations they suffer, how this force expresses itself on the two of them, the relative size of the droplet and the rail car, etc. And then we'd have to do that for every single droplet over a 30-minute interval. Could you do this in principle? Sure, it's just some nasty kinematics, some dynamics, and some calculus. But it's pretty messy, and we'd like a way of doing problems like this simpler, and we don't really care about the forces in between. We care only about the beginning and end of speed. You might be tempted to do an energy analysis, but we have internal forces going on here that can take energy out of the system, right? Or at least take kinetic energy out. In other words, we know that the energy is not going to be conserved because ultimately the cart is moving slower and the water is moving over to the right. So we need a different technique. We're going to tackle a different problem first and then come back to that one. Let's take a puck hit by a hockey stick. While the puck is in contact with the stick, it exerts a force F average on it, causing it to accelerate. From the Newton's second law, the average acceleration is just the average force over the mass. From kinematics, the average acceleration is the change in the velocity over the time. Using the transitive property, this must equal this. F average over m must be delta v over delta t. And we can rearrange that to say that the average force times the time is the mass times the final velocity minus mass times the initial velocity. This has so far been just a bunch of algebra, but it's going to end up being quite important. To repeat, we have ft average times delta t is the same as mvf minus mvi. The thing on the left is the impulse delivered by the stick. That's what we talked about in the last thing. The right-hand side is clearly the change in something, because it's a difference of two things, a final minus initial. We call that something momentum. And we symbolize it by the symbol P. Lowercase p for an individual object, and usually capital P for a system. Important to note that momentum is a vector, because impulse is a vector. Historical side, Newton revolutionized dynamics in part by considering what he called the quantity of motion, which he took to be mv. Notice no vector sign. This is almost, but not quite, like momentum, because he had a scalar. But both of them give definition to the intuitive sense that a heavy object moving slowly and a light object moving quickly can, in some manner, be considered equivalent. Momentum is a fundamental property that any physical object has, although its value could always be zero. As with kinetic energy, any object that has velocity has a non-zero momentum attached to it. As an example, which has the momentum with the greater magnitude, a 10-gram ball moving at 10 meters per second, or a 1 kilogram object moving at 1 meter per second? Here we just run the numbers. 10 grams times 1 kilogram per 1,000 grams, that's going to be an important conversion for comparison, times the speed, ends up being a tenth in these weird units, kilogram meters per second, whereas P2 ends up being 1 kilogram meter per second, and so we see the 1 kilogram object has more momentum. We derived that early result for average forces and finite time intervals, but it turns out it works for any forces and any time intervals, that the change in momentum is always the impulse delivered during an interaction. So the change in momentum during some interaction is the impulse delivered during that action. This will end up being the thing that lets us solve, for instance, our railcar problem and some others.